Welcome to Physics Made Easy channel. We will do important points, even shortcuts and pitfalls for related to various topics. Basic purpose is to focus on the concepts. And first of all, I will revise some of the formulas. Microscope and telescope. Note this point, limit of resolution. And also note the one point that limit of resolution and resolving power, they are not the same. They are reciprocal of each other. For example, here the formula for limit of resolution d is equal to lambda by 2 mu sine theta. Note down, this is for compound microscope. This is the compound microscope formula is for this. And now limit of resolution is d. Resolving power Rp. Resolving power is 1 by d, and this will be equal to 2 mu sine theta by t. Next is resolving power of compound microscope. This he has given limit of resolution. Remember, this is limit of resolution. In the very next step, resolving power. Resolving power of compound microscope is this. Mu sine theta is numerical aperture. Mu sine theta is numerical aperture. Limit of resolution of an astronomical telescope d theta is 1.22 lambda by capital D. Resolving power of astronomical telescope 1 by d theta is equal to d by 1.22 lambda. Units use lambda, small d and capital D in meters. Theta, d theta and mu has no units because these are merely ratios. Again note down the resolving power of astronomical telescope is 1 by d theta is d by 1.22 lambda. The limit of resolution is 1.22 lambda divided by d. Now you will not be asked trivial questions like this. Calculate the resolving power of microscope if its numerical aperture is 0.2 and wavelength used is this. A telescope is used to resolve two stars separated by this. Now telescope d theta is given in this case. We know this formula, d theta is 1.22 lambda. Now this d theta is given. D theta is given how a telescope is used to resolve two stars separated by this radiance. If the wavelength of light used is this, what will be the aperture? Trivial question. Calculate the separation of 2 points on moon that can be resolved using a telescope of 600 centimeter. Given the distance of moon from this and this, all these are trivial questions. So only one thing is this, he has given us limit of resolution. Now from limit of resolution, here I want to draw the graph. Now note down this. Here he has given limit of resolution of this. Now it is the case of a telescope. If d theta is such an angle like this, d theta, and this distance is given to us. This distance is capital D. This distance is capital D, or the radius vector is capital D, then obviously x divided by capital D is equal to d theta. This capital D is dm, I will write, distance from moon. So in this case, he has asked us linear distance dx multiplied by distance from moon. More accurately, I will show you this diagram. This is the case of a telescope. Now this d theta angle is given. D theta angle is given. D theta angle is given. If this distance is given, we can find out this separation of linear separation of O1 and O2. D theta is given. This capital D is distance from moon, that is also given. And we can find out separation between these two objects. That can be seen as result. So this is a brief concept. Now, in this problem, he is given a telescope, diameter of telescope is given. In this very problem, diameter of telescope capital D is given, the focal length of the objective and eyepiece, they are given. Telescope is directed to view two distant almost point sources of light, two binary stars. The sources are roughly at the same distance, 10 raised to power 4 light year. Distance is given along the line of sight, but separated by a transverse distance of 10 raised to power 10. Now, in this problem, what is important is he has given us this point and then this transverse distance is given. This angle we want to calculate d theta. And this distance is also given, 10 raised to power 4 light years. This distance is given. This distance is given. If we will divide this by this, we will get this angle d theta. So let it be capital X. I will say this as capital X. And this distance as you can say d. So now here this d theta is the actual angle made by an object at I. Now we will find out limit of resolution. If limit of resolution is less than this, then it will be resolved. If more than this, now I will write if limit of resolution LOR is greater than d theta, image will be resolved. Objects will be resolved. Image of the objects will be resolved, or you can see the objects as separate. But if limit of resolution let me make here a correction. If limit of resolution is less than this, then it will be resolved. If limit of resolution is more than this d theta, that is d theta is 10 degree, suppose limit of resolution is say 20 degree, then it won't be resolved. So if limit of resolution is less than the actual angular separation, then it will be resolved. Here it is 10 raised to power minus 10 radians, and d theta is 10 raised to power minus 6 radians. So this d theta is smaller than this angle subtended. So that's why telescope cannot resolve it. So this kind of concept is important. This is important for, you can say, JEE main and even advanced. This concept is important for JEE main and advanced. The concept is you have to calculate limit of resolution and you calculate the actual angle subtended by the two objects on the telescope. If the actual angle subtended is more than limit of resolution, then Object is resolved. If it is less than limit of resolution, then object is not resolved. This is a very important and dangerous concept. Calculate the resolving power of microscope with cone angle of light falling uh, on an object is 60 degree. Cone angle is 60 degree. It means this is a microscope. Now in this case, cone angle theta is given to be 60 degree. It is 2 theta and theta comes out to be 30 degree. This is the only catch point of this article. This is the only catch point of this article. Otherwise, it's quite simple and such questions can be asked in JEE mains. We can easily find out the resolving power. Next is, assume the light of wavelength is coming from star. What will be the limit of resolution of telescope with 10 inches in diameter? Inches, it is board level question. You just convert inches into centimeter. And this conversion 1 inch is equal to 2.54 centimeter is important. The diameter of pupil of human eye is 2 mm. Human eye is most sensitive to this wavelength 555 nm. Find the limit of resolution of eye. Lambda is given and D is given. You can easily find out. I don't think there is any problem. A laser beam has wavelength of this and aperture of 10 raised to power minus 2 meter. A beam is sent to moon. The distance of which from earth is this. Find the angular spread and the aerial spread. Yes, a laser beam of wavelength lambda is given. Lambda is given. And aperture is given. If lambda is given, aperture is given, you can find out the angle. So what we are finding out, we have found this angle, theta. Now, once we have found this angle theta, this is the angle theta. This angle theta is given and this distance is given. This distance is given. Now aerial spread is you just find out this distance and takes care of it. And here we don't multiply with pi. Why don't we multiply with pi? Because this is angle is in radians. Angle is in radians. If you take angle in degrees, then you will have to do that. So this will give you the aerial spread. Aerial spread is the base of the cone. Like this. And next part is Doppler effect. It's very important effect, Doppler's effect. So we have got two formulas for Doppler effect. Note down the formulas are same. There is just a difference of a positive and negative sign. First is change in frequency divided by frequency. Note down this formula. Delta nu divided by nu is equal to plus minus V by C. Delta nu is frequency. I generally write it in this form. Delta n by n is equal to plus minus V by C. And then if we write the same formula in terms of wavelength, then minus comes first and plus comes after that. Velocity of an aeroplane, rocket or submarine, there is correction of by 1/2. Minus plus 1/2 delta lambda by lambda into C and plus minus 1/2 delta nu divided by nu into C, where nu is in hertz. V and C is in meter per second and lambda is in meters. Earth is moving towards a fixed star with a velocity of 30 km per second. An observer on Earth observes a shift of 0.58 angstroms in wavelength of light coming from star. What is the actual wavelength of the light emitted? Now, all the questions on this topic that are asked from you are trivial. Earth is moving towards a fixed star, velocity is given. An observer from the Earth observes a shift of this. Shift is given, delta lambda is given, and velocity is given. C we already know. Then you can find out the wavelength. I don't think if there is any problem. Delta lambda by lambda is equal to V by C. V is equal to delta lambda by lambda multiplied by C. No issue at all. A radar wave has a frequency of this. The reflected wave from an aeroplane shows a frequency difference of this. Delta nu is given and nu is given. Again, a very easy question. Now, only one thing is to be noticed. Here, radar. When we use a radar, in velocity of aeroplane, rocket or this factor half comes. This is to be noticed. If we are talking in terms of stars, then this factor 1 by 2 never figures. This factor 1 by 2 figures only if we are talking about aeroplane or rockets. So before ending this lecture, there are one or two more problems. I would like to go through them. So there is nothing new about this thing. With the speed of light, galaxy should be this. This is again a very important problem. Now, I would like to summarize this lecture. So what are the important points that we got from whole of this lecture? One is limit of resolution is opposite of resolving power. First point, notice, and this mu sine theta is numerical aperture. Mu sine theta is numerical aperture. Limit of resolution is opposite of resolving power. It is distance in case of compound microscope, and angle d theta is limit of resolution. 1 by d theta is resolving power. It is the case of telescope. D is limit of resolution and 1 by d is resolving power. This is the case of a compound microscope. Now let us proceed ahead and note down this thing. This d theta, this we may need to find the angle subtended by a distant object, and for finding that, x divided by the distance of the object from the telescope is equal to the angle d theta. This has been used many times, and also sometimes the angle of the cone is very important. This d theta, again the formula that we have used earlier, x by d is d theta. If the angle subtended d theta is more than the limit of resolution, then object is resolved. If it is less than the limit of resolution, then object is not resolved. This is the only important point that we have come to know. In case of microscope, the angle theta that we use in numerical aperture 2 mu sine theta is half of the cone angle. Cone angle is 2 theta. Angle theta, which appears in the expression of compound microscope, is half of the cone angle. And rest, when we are dealing with Doppler effect, only remember one point. When we are talking about wavelength shift or frequency shift between the two fast moving stars or planets, then you have to just use the formula plus minus V by C in case of frequency, minus plus V by C in case of wavelength. If it is the case of aeroplane, rocket or submarine, then you have to add this factor 1 by 2 in front of it. With these words, before finishing this lecture, I will request all of you to kindly go through this video, pick up the important point, make up the notes. They are, if you don't remember, then they may become pitfalls for you. If you like the video, then kindly share it. If you don't like, then kindly comment. With these words, I finish this lecture and we will meet in the next.